Good morning, everyone. My name is Syuan-You. I'm a PhD student working with Dr. Shinsuke Akihara. Today, I'm going to present one of my PhD study, Foliar application of urea and lime sulfur for seasonal extension of subtropical blackberry production. Berry crops are low-carbohydrate fruit. They are considered a superfood that packs major nutrients with bright flavor and intense color. Among them, blackberries are rich in phytochemicals, including anthocyanins, flavonoids, which can protect against heart disease, cancer, and diabetes. There's a growing demand of blackberry because of the new varieties with improved aroma and flavor. And blackberry is so popular and that it is the fourth most economical important berry crops in the United States and result in $549 million in retail sales in 2016. The import of fresh blackberry increased from 43 million tons in 2010 to about 74 million tons in 2017. In the US, blackberry production concentrated in Oregon and California. There has been also a growing interest in producing blackberry in southeastern United States. The growing area increased from 2,000 acres in 2007 to around 4,000 acres in 2017. This trend was shown in Florida, particularly in Central Florida. However, the commercial blackberry production is still limited to local market and U-pick operation. Blackberry is a deciduous fruit crop and is well adapted in temperate climate. In Florida, its reproductive phenology is about 1 month earlier than the plant grown in temperate regions. Generally, Budbreak occur in early March to early April, and flowers will be observed about 2 weeks after the Budbreak. At about 6 weeks after the flowering, fruit will be ripening in early May to June. Like most decidual fruit crops, winter chill plays an important role in Budbreak and flower development in blackberry. In general, blackberry plants defoliate naturally and develop flower bulbs on primocane in late fall, and bulb will enter into dormancy during the winter. And they will sprout in the upcoming spring. And plants must be exposed to a certain amount of winter chill to break bulb dormancy in spring. This is so-called chilling requirement, which is highly variable among blackberry varieties. The chilling requirement of commercial blackberry cultivars varies from 300 to 900 hours below 7 degrees Celsius. In subtropical climate, blackberry production has two challenges. First, inadequate chilling cause poor and erratic bulb break. And second, the season harvest coincide with high temperature and heavy rainfall, deteriorating fruit quality by sun scarred, rain damage. So for viable subtropical blackberry production, dormancy should be artificially released to accelerate bulb break and to advance fruiting season. Many chemicals have been tested and developed as dormancy breaking agent for temperate fruit crop, and various defoliants are commercially applied to promote bulb break and advance flowering time. Among them, the most successful one is hydrogen cyanamide, HC. In the past 2 decades, hydrogen cyanamide application has become a primary commercial practice in peach and in blueberry production in Florida for breaking bud dormancy. And hydrogen cyanamide can induce oxidative stress and increase the production of gibberellic acid and cytokinin, and in turn inhibit AVA production, and it also upregulates the expression of flowering and Budbreak related genes. All of these responses also occur naturally during the natural Budbreak. The major drawbacks of hydrogen cyanamide are its adverse health effect and potential environmental pollution. As a result, hydrogen cyanamide application is strictly regulated or even prohibited in some countries. For example, in European Union has banned hydrogen cyanamide since 2008, and New Zealand is reviewing its regulation this year. The ideal Budbreak engine should have not only high efficacy, but also a low risk safety profile and low application cost. Some fertilizers, such as urea, is reported to be highly effective in defoliating fruit crops. Their Budbreak induction effect have also been reported in many fruit crops. For example, in cherimoya, Budbreak could be advanced by 3 weeks, flowering advanced by 2 weeks, and fruit earnings could be advanced by 12 days by using 8% of urea. However, the efficacy of defoliant in breaking bud dormancy has not been tested in Blackberry. So in this study, the objective was to examine the dormancy breaking effect of urea and lime sulfur in not just Blackberry under subtropical climatic conditions. We performed 2 field experiments to examine the bud breaking effect of these 2 defoliants. And we have 2 different experiments. One, we apply defoliants in December, and the second experiment is we apply these 2 defoliants in mid-February. The defoliant was sprayed at 10% with a spray volume of 100 gallons per acre by using a CO2 pressurized backpack sprayer. All data were analyzed by the generalized linear mixed model procedure as implemented in the SARS. And we will sample like 2.5 feet long cans with about 25 nodes. And we will record sprouted bulbs, unsprouted bulbs, and leaf number weekly to calculate the percentage of defoliation and Budbreak. And during the harvest, we will harvest berries twice a week. And in February application, we sample bulbs from the untreated control and lime sulfur at 3 and 6 days after application to quantify and qualify the hormone labels. And we analyzed the continuous percentage data in a beta distribution, and we analyzed continuous data like yield and hormone concentration in novel distribution. In December application experiment, urea and lime sulfur induced rapid defoliation at around 7 days after treatment, ranging from 60% to 85%, compared with the 40% in the untreated control. The percentage of defoliation remained higher throughout the experimental period. Budbreak could be quickly observed at 7 days after treatment in urea, followed by the lime sulfur at 40 days after treatment, and the untreated control did not show any Budbreak until about 2 months after the treatment. The final percentage of Budbreak was highest in lime sulfur, followed by urea and the untreated control, although no statistical significance was detected among the treatment. We started to harvest Blackberry in the urea treated plot beginning from the early April. In lime sulfur and untreated control, first harvest was delayed by about 3 weeks compared with the urea treatment. Overall, the total yield was similar between treatments, averaging at 2.5 kilograms per plant or 5.5 pounds per plant. In February application experiment, although the urea and lime sulfur induced numerically higher percentage of defoliation, their differences were not statistically significant throughout the experimental period. Budbreak was rapidly induced by the urea and lime sulfur treatment at about 2 weeks after treatment. The lime sulfur treatment induced the highest budbreak, followed by urea and the untreated control. In the most of the time, lime sulfur treatment showed significantly higher budbreak than the untreated control. However, in the end of the data collection, the percentage of budbreak was not significantly different among the treatment. The marketable yield among the treatment was similar among the harvest timings. However, the lime sulfur increased about 60% of yield compared with the urea in the untreated control. Jasmonate, methyl jasmonate, and abscisic acid are involved in many stress responses, including defoliation and dormancy. Compared with the control, lime sulfur treatment in mid-February had no effect on jasmonate labels, but it increased the labels of methyl jasmonate by about 1,560% at 3 days after the treatment, but this difference diminished at 6 days after treatment. AVA label was marginally different among the treatment at 3 and 6 days after the treatment. The lime sulfur treatment also increased the IAA labels by about 265% at 3 days after treatment and by about 300% at 6 days after treatment. GF4 labels was not significantly different among the control and lime sulfur treatment. In addition, we tried to quantify GF3 content, but we could not detect GF3 in this study. Figure 8 shows a hypothetical models of dormancy release in which hormones, metabolism, oxidative stress, and transport capacity of cell wall play important roles in dormancy release. We found dormancy breaking agent may affect mostly on the ROS production and also induce the ethylene production to inhibit the AVA and also induce some growth-related hormones like gibberellic acid, auxin, cytokinin. A recent study documented that chemical defoliation by TDZ, which is a cytokinin-like plant hormone, can cause the increase in ROS and ethylene production on cotton. We postulate in our study urea and lime sulfur-induced defoliation will trigger similar responses in Blackberry. In December, we observed urea can induce more rapid defoliation, which might cause greater stresses, which in turn induce early budbreak. In February application, plants were close to the timing of natural budbreak, so the defoliation effect of our treatment might be small. We observed lime sulfur had more budbreak. This might be associated with the observed increase in methyl jasmonate and IAA labels. And we also postulate that the sulfur compound in lime sulfur may help increase the percentage of budbreak because it is reported to have dormancy breaking effect in table grape and apple. So under the natural condition, the blackberry harvest occurred from early May to June in Central Florida. With the defoliant application, seasonal extension can be achieved. Urea is highly effective in inducing budbreak and increasing early season yields, so it would be a good strategy for seasonal extension. Furthermore, lime sulfur can max by budbreak, and fruit yields when applied after chill acclimation, let's say in February. So it might be a good strategy to increase yields under inadequate chilling conditions. I would like to thank our funding source, specialty crop block grant, and all the collaborators from my PhD research committee, chemical dynamic, and the Fancy Fund for providing plant materials and experimental site. And I would also like to thank all the staff in Horticultural Physiology Crop Lab in GCIEC. And thank you for your attention. And feel free to let me know if you have more questions or comments via email or my LinkedIn.